Hello everyone and welcome. I'm Tim from Premium Tutor. In this lesson, we're going to explore one of the most beautiful and subtle ideas in all of calculus, the idea of a limit. You see, mathematics often asks questions that can't be answered by direct substitution or by simple arithmetic. Instead, we ask, what happens as we get closer? As x approaches a value, how does f of x respond? Does it settle toward a single number, or does it drift away, perhaps to infinity, or even oscillate without end? Limits give us a precise language for describing these behaviors, how we make sense of continuity, how we define derivatives, and how we begin to capture change itself, one of the most central ideas of calculus. So in this first part of our journey, we will slow down, take a careful look at what it means to approach a value, and discover why this seemingly simple concept is the key that unlocks so much of modern mathematics. Let's begin. Here's a function that looks pretty normal until you get close to x equals 1. See that little gap? The graph breaks because the denominator becomes 0, so the function isn't actually defined there. But if you follow the curve from both sides, the values seem to settle toward the same spot. That's the beauty of limits. They let us describe what a function approaches even when it doesn't quite get there. Now, let's look at what's happening with the numbers. As x gets closer to 1 from the left, 0.9, 0.99, 0.999, the values of f of x move toward 0.5. From the right, 1.1, 1.01, 1.001, they do exactly the same. So, from both directions, the function approaches 0.5. That means the limit as x approaches 1 is 0.5. Even though the function has a hole there, its behavior is clear. It's heading straight toward that value. We can sum this up pretty simply. As x gets close to a, f of x gets close to L. It's not about what happens exactly at a, but what happens around it. That idea, focusing on how things behave as we approach a point, is really where calculus begins. Let's try this idea with an example. We're estimating the limit as t approaches 0. If we plug in small values of t, both positive and negative, the results start settling around 0.166666, or just 1 over 6. Notice we didn't need to plug in t equals 0. We just looked at what values were doing as we got closer. That's the power of limits. They show us how a function behaves near a point, even when the function itself isn't defined there. Let's look at a simple but interesting example, the Heaviside function. It's 0 for all values of t less than 0, and 1 for all values greater than or equal to 0. What's special is that sudden jump at t equals 0. From the left, h of t stays at 0, from the right it jumps up to 1. This difference between the two sides show how limits help us describe sharp changes in a function's behavior. To understand this better, we use the idea of one-sided limits. For a limit to exist, both sides, the left-hand and the right-hand limits, have to agree. If they approach different values, then the limit doesn't exist. That's really what continuity depends on, both sides of the graph meeting at the same point. Let's use this graph to explore one-sided limits. So you see, each part of the curve behaves a little bit differently. So as x approaches 2 from the left, the function value approaches 3. As x approaches 2 from the right, the function value approaches 1. Since the two limits do not agree with each other, the limit of g of x as x approaches 2 doesn't exist. On the other hand, when x is around 5, the left-hand limit and the right-hand limit do agree with each other. they're both equal to 2. So the limit of g of x as x approaches 5 is equal to 2. Well, sometimes a limit just doesn't exist, and that's not an error. It simply means the function behaves in a more interesting way. There are 3 main reasons this could happen. First, a jump discontinuity. When the left and right sides approach different values and the graph suddenly jumps between them. Second, an infinite discontinuity. When the function's values shoot up or down without bound, forming a vertical asymptote. And finally, oscillation, where the function keeps swinging back and forth like sine of 1 over x near 0, never settling on one value. So when a limit doesn't exist, it's not because math fails, it's because the function has more to show us. Let's look at the really interesting example, the limit of sine 1 over x as x approaches 0. As x gets closer to 0, 1 over x grows huge, positive on one side, negative on the other. The sign of that value swings rapidly between -1 and +1, faster and faster, without even settling down. So the function never approaches a single number. The limit doesn't exist. It just keeps oscillating endlessly between those two extremes. Now let's look at a different kind of behavior, when a function doesn't settle or oscillate, but instead shoots off toward infinity. If f of x gets larger and larger as x approaches some value a, we say the limit of f of x as x approaches a is equal to infinity. That simply means the closer we get to a, the bigger f of x becomes, with no upper limit, no boundary, just continuous growth. Functions can also go the other way, dropping down toward negative infinity. We write that as limit of f of x equals negative infinity, meaning f of x can become as small or as negative as we like as x gets closer to a certain point. In both cases, whether it rises or falls, the idea is the same. There's a point we can approach but never reach, where the function shoots off endlessly. These are called vertical asymptotes, the invisible boundaries that define how a graph behaves near its limits. Here's what that looks like on a graph. As x approaches 1 from the left, f of x drops sharply downward. From the right, it rises steeply upward. The line x equals 1 isn't really a barrier. It's more like a boundary the function can approach but never cross. That's what we mean by a vertical asymptote. The function keeps getting closer, but there is nothing beyond that line. In this example, let's find a vertical asymptote for the function f of x equals x plus 5 over 2x plus 4. A vertical asymptote happens when the denominator becomes 0. That's where the function tries to divide by nothing. So we set 2x plus 4 equals 0, which gives x equals -2. At x equals -2, the numerator isn't 0. Instead, it's 3. So this point is not a hole. It's actually an asymptote. That means the line x equals -2 is where the graph shoots up or down without bound. It's that invisible line the curve can approach but never cross. Alright, let's take a moment to sum everything up. A limit is all about approach, not arrival. We care less about the exact value and more about what happens as we get close to it. Sometimes both sides of the graph approach the same value, but sometimes they don't. And when they don't, the limit doesn't exist. That can happen in 3 different ways. Number 1, a jump, where the function suddenly leaps to another value. Number 2, an infinite discontinuity, where it shoots off towards infinity. And number 3, oscillation, where it keeps switching endlessly without settling. Infinite limits, in particular, are what create vertical asymptotes, those invisible lines the graph can approach but never cross. In the end, limits aren't just about numbers. They're about how functions behave as we get closer and closer to something we can't quite reach. And that's where we'll wrap up this lesson. We've seen that limits aren't just a rule or formula, they're a way to describe how things behave as they get close, how math captures motion, growth, and change with incredible accuracy. From functions that smoothly approach a number, to those that jump, oscillate, or head off towards infinity, limits give us a precise language for describing what happens near the edges of understanding. This idea of approach is the foundation of calculus. It's what leads us to continuity, derivatives, and everything that follows. If you'd like to keep going, check out our next lessons on derivatives and the applications of limits. And if you have any questions, feel free to reach out. We'd love to hear from you. And don't forget to like, subscribe, and share the video with anyone starting their calculus journey. I'll see you next time. Cheers. Bye.